So let us start with the building overview. For the 3D model, this is the 3D model of our structure. So we have this chevron brace and the ramps. And this is the typical floor plan, reflecting the dimension of or the distance between columns to columns. So we also have the intermediate beam intersected at third points, and this portion is for the ramp. So at grid line 1 and 4, this will be the configuration of our framing. At grid line 2 and 3, grid line A and H, as well as grid line B to G, with a typical floor-to-floor height of 3.2 meters. So for the design criteria, we'll be using, of course, NSCP 2015, which is also related to UBC 1997, as well as IBC 2012 or ASCE 7-10. For the structural steel, we'll be using A992 or ASTM A992. The design load for the dead loads, we have the deck slab, which is 2.94 kPa, the metal deck, 0.14 kPa, the waterproofing membrane, 0.07, and for the live loads for parking structure, we will consider 4.8 kPa. The seismic loads or the static seismic load importance factor is 1. Soil profile type SD and the distance from West Valley Fault system at 10 kilometers, zone factor Z at 0.4, and the seismic source type A. And lastly is the ductility capacity R for the especially concentric brace frame, which is 6. And the dynamic seismic load, considering UBC 1997 code or the NSCP 2015. For the wind loads, again, the importance factor is 1, the basic wind speed is 250 kph, the exposure category is B, and the directional and gust effect factor will be 0.85. All in all, for the parking and ramps, we will consider the dead load and live load of 3.15 and 4.8 kPa respectively. So these are some of the load combination that we will be also using here in our design for the LRFD. And the minimum densities for design loads coming from table 204-1 based on NSCP 2015 and the minimum uniform live loads that you can consider. So as you can see, for the parking, we have the 4.8 kPa for the uniform load. So let us start with the actual modeling. So let me go to the MIDAS gen file. So I will just create a new file. So after creating a new file, let me just save this as steel Carpark. And now we can just define the material. So let me go to the properties tab, material properties. I can now add the materials. So since I am designing a steel structure, I will be selecting steel. And for the standard, let's say I will be using ASTM 09 based on our design criteria. And for the database, let me use A992. So I can now just click on OK, and it is now reflected in the material properties dialog box. So for the section, same with the material definition, I can just add. And since we will be using here in our structure an I section and a T section, so I will just first select the I section. And from the database, I will be using AISC. So for column, let us say we will be using W14 by 120. So I can just click on apply. And the name is also updated here. So for the main girder, so let's say W18 by 71. For the intermediate beam, I can just use, for example, W14 by 61. And lastly, for the chevron brace, let me use a T section. So for the T section, same with the database AISC that I will be using. So let me say I will be using WT7 by 21.5, and I can just click on OK. So these are the 4 sections that I will be using here in the case study. So I can just close this and let us start with the actual modeling. So for the actual modeling of our structure, there are different types of actual modeling that you can use or you can do. So first, you can just import the DXF file. So some engineers do this, import the DXF file, or sometimes they created a grid line. So you can just create your grid line. And also some engineers create nodes, and these nodes are then translated into different directions to create the columns, the beams. But here in the case study, I will be using a different approach, which is using the structural wizard. So here in the structural wizard, it is in XZ plane, but here in the plan, actually the vertical axis in MIDAS is the Z axis, and later on, since we are dealing the frame wizard into XZ plane, we will translate this later into XY plane. So let us check first the plan. So these are the dimension along x-axis, and these are the dimension that we'll be inputting into the z-axis. So for the x-axis, we have 5. So number of repetition is 1. And the next one is 7.5, 6.5, the 5 meters, as well as the 6, the 7.5, and the last bay is 8 meters. So all in all, it should have the 45.5 meters along x direction. So in z coordinate, again, I'm stressing this out. I will be translating this into xy plane later. So for the distance along z axis or y axis later, it is 7.2 and 2 base at 6 meters. So 7.2, number of repetition is 1. And the next is 6 meters and the number of repetition is 2. So after we have created the supposedly columns here in our structure, I will now go to the edit tab, just create or generate the frame. So this is the initial framing that we want to see actually in the XY plane. And since it is in the XZ plane and we will translate it to XY plane, we should also translate our element or the individual element. So the beta angle that I will be using is 90 degrees. For the material section, I can just use A992. And for the base section, let's say W18 by 71. So for the insert tab, so let's make sure the insertion point is 0, 0, 0. And the rotation, the alpha, beta, and gamma stands for the rotation along X, Y, and Z respectively. So since I am doing this frame into XZ plane and I want to transfer it into XY plane, I will just change this into negative 90 degrees. So I can now just click on apply and close. So after we have created the initial framing or the supposedly second floor of our structure, let me go to top view. So here, based on our plan, it should be open in this portion which the ramp is located. So I can just select this portion of the beams and just delete it. So let me use the select single, delete these columns, selecting this just like an AutoCAD option from right to left or left to right. There is a specific option that you can do. Delete, and now after I have deleted this, I can now also create our column. So to create our column, I'll just go to the node and the element tab, and there is the extrude option. So since I am creating a column, so what I will do is node to line element. If I want to create a wall, there is a line to planar element. And for solid elements, we can just do the planar element to solid element. So again, I'm creating a column, so I will just choose node to line. And the material that I will be using is A992. The section for our column is W14 by 120. Let me just change the beta angle into 90 degrees so that it will be along y-axis. So for the distance, since I want this portion or this framing as my second floor, I will just make or translate the element negative 3.2. So since 3.2 is the typical floor-to-floor height of our structure, so negative 3.2 along z direction. So let me just select all the element first, and as you can see, all of the nodes are being selected, and this will be the generated column. So as you can see, this is the column that we have already generated. So next, we want to verify that the section is actually applied on to the specific element. So what we will do is to just change the section to make it easy for us to check the specific section into our model. So display option draw, I will just use the section per thickness color. So let me just choose a good color into our model. So let me just use this one. So you can just change the color if you actually apply random color and then apply. So that's an example. So after I change the color of our structure, what I will do next is to apply the intermediate beam. So to apply the intermediate beam, so let me just click the create elements, making sure that the element type that I will be using is a general beam or tapered beam. And for the intermediate beam, we'll be using, for example, W14 by 61, a little lighter from the main girder. And let me just uncheck the intersect first for the nodes as well as for the element. So since in our structure, in our framing plan, it is actually divided into third points. So I will just change the intersect option here. So since it is, or the snap will be into midpoint, so I will just change this into 3 so that it will be intersected every third points. So let me just create the element. So let me just check also the framing plan. So this is the configuration. So creating the intermediate beam. There you have it. So after we have created the intermediate beam, so next is the ramps. So let me just again intersect this. So as you can see, it will first let me check or let me show you if it is, for example, it is not intersected. This is what we actually did before. And now if we want to intersect this, so creating again an element using this section for the ramp. So if I select this, it will now be intersected among the elements or the nodes. So what I will do now is to create the ramp. So I will just translate these ramp beams. So let me just use the select single and select these elements. And there is a translate option that you can use here in MIDAS Gen. So what I will do is copy. And for the unequal distance, so the distances that I will be using is 0.3, a little offset from this portion. And the next is 2 at 3.3. And the last one is 0.3. So I will translate this into y-axis. And making sure that it is also intersected, I will just check the node and element. So I can now click on apply. So after I have created the beams for the ramps, what I will do next is to delete the portion of the ramp that is not actually part of the model. So let me just use the zoom by window, and using the select single, I can just select the outer portion of the ramp. So using the delete key in our keyboard, you can easily delete the elements. So after we have deleted the elements, we can just also create the beams here connecting the ramps. So let me go to this view, and again I will just use the zoom window, zooming in or focusing in this portion only of our structure. So create elements again. I will now be using W18 by 71 here, and I will just connect these elements. So after we have created the beams intersecting the ramp elements, so what we will do now is to also intersect, because we do not intersect the beams initially in this portion. So we will just intersect the beams. So let me go to the isometric view first, and I will use the select by plane. Along XY plane, I will just select a point. So as you can see, it is now highlighted. I can just close this and activate this portion or part of the framing that I have already selected. And going to the top view, I can now also apply the releases, because here in steel structure we often apply release. So let me just apply the releases. So going to the boundary tab, and there is a beam end release. So I will just use the pin connection. So using the select single, I will just select this element. Sorry, I will just intersect first this element. So from the node and the element tab, there is actually an intersect option that you can do if you forgot to intersect the elements. And then I will just apply, and it will now be intersected. So again, I will apply the beam and release. So going to the boundary tab, beam and release, using pin connection, and I will just select the specific element which I want to release, which is along X direction. So after that, I can now click on apply. So let me view the symbol for the release. So the boundary tab, just click the beam and release symbol, apply. So it will have a green dot on the support. So after I have added the beam and release into our model, so what's next is to apply the chevron truss. So let me view first all of the structure. We also forgot, we should also apply the beam and release here. So again, using select single, I will just select this portion or these elements. So click on apply. So after we have applied also the releases into the ramps, we can now apply the chevron brace. So to apply the chevron brace, I will just create again a new element or create element. So what I will do now is to select a truss or use a truss element here. And for the section, we can use WT 7 by 21.5, and I can just uh, create the chevron brace. But let me change this into midpoint so that it will snap into midpoints. So connecting this into the midpoint of our structure, as well as here in this portion, So let us check the configuration of our building. So this is at grid line 1 and 4 and grid line A and H. So as you can see, we are now adding the chevron brace into our structure, the bracing of our structure using a truss element. So after adding the chevron brace, so let us just rotate and check if we applied it correctly. So after we have applied the chevron brace into our structure, so what's next is to define the ground level. So we can just define the ground level in the structure tab, and then from the control data, so we can just use the ground level. So with this, we can specify which is the ground level for us to consider in the lateral forces later on that we will be apply into. So negative 3.2 for the ground level. So as you remember, so this is the origin of our structure, and we extrude our column negative 3.2 below. So suppose this is the ground level of our structure, so I will just use the negative 3.2. Clicking on OK. And now we can just generate the building, or we can now use the building generation. So this is actually some of the strong point of MIDAS Gen. So you can easily copy floors using the building generation. So for the number of copies, I will just input 3. And the distance, as I've said before, based on our configuration, it is 3.2 meters floor to floor height. So selecting all the elements, so clicking on apply. And now you can see that the building is now generated. So it is actually copied. All of the materials or section is now copied. But as you can see also here in MIDAS Gen, if you want to change, for example, as you uh, generated the floor and you want that the material is decreasing, for example, from the lower floor it is 4,000 psi, and the next floor you will be considering 3,000 psi only, you can just add the material increment as well as the column section increment, beam section, wall, as well as the brace. You can just add an increment if you want to change the generation of your structure from this or the element or the properties upon generating the building structure. So after we have created the the whole structure, what I will now do is to create a story. So this is the story. So I will just create the or auto generate the story. So this purpose is to determine for the seismic load as well as the lateral forces to our structure, which is the floor to be considered. So I can just select the unnecessary floor and move it to the unselected list. And this is the consideration or the floor levels that I want to be considered when I apply the lateral forces. And also you can consider or do not consider easily the diaphragm. So after we have created all the story, so let me just check. So this is the ground floor. So after we have checked the or created the story, we can also check if all the elements are intersected. Again, same as before, we can just go to the node and element tab using select single. And now I will select all the structure, intersect all the elements. So it is actually important to intersect all of your elements, so you will not get an error upon analyzing your structure. So I can now just click on apply. And of course, we can also clean our model. So how to clean our model if there are, for example, a duplicated elements, you can just select all of your structure, and there is actually a check duplicate element. So as you can see, there are 18 elements have been deleted, and because of the duplicated elements. So after we have checked the duplicated elements and intersected the model, we can also apply the boundary condition. So let us select first all the columns. So going into the toggle work tree, and then I will just click the columns that I have created. I can now just use the activate. So all of the columns are now activated. Going to the front view, and now I will add the boundary conditions. So boundary condition, define support, we have the D all and DR all. So what does it mean? So actually the boundary condition here in MIDAS Gen is this. So for the green symbol, meaning it is constrained, and the black symbol, meaning it is released. So this is the rotation of the configuration of the support. So dx, dy, dz, rx, ry, and rz. So green constrained, black release. We will apply this into our model. So to apply this into our model, so what I will do is first I will be using a pin support into our structure. So the displacement will be constrained if I want to use a pin connection. So using a select single and selecting all the bottom nodes where I want to apply the support, I can now click on apply and check if it is already applied. Support. Sorry, I selected that one. So again, so these are the support that we will be using into our structure. So let me just unshow the support. So after we have created the support and apply the release, we can just view all of the structure and go to the again the typical view of our structure, which is on XY plane, or I mean the isometric view. So viewing the isometric view, what we will do now is first we can define the static load or the basic static loads. So I can now go to the load tab, static loads, and then define the basic static load cases. So here in our case study, I will be using basic load cases or the static load cases. Like the dead load, I will just select the load type as dead load. I also have the live load. So load type is live load, WLX, for example, a wind load on structure, wind load along Y, EQX for the earthquake, and EQY. So these are some of the basic static load case. But of course, if you will be going to design or fully design your structure, you must consider the different types of load that you will be applying into your structure. This is just for the sake of the case study that I will be showing you here in this webinar. So after applying the basic static loads, I can now just close this button, and of course I can define the or convert the self-weight into masses. So where do I find that? I can just go to the structure type, and then there is a convert self-weight into masses. So I can just convert it into XY axis. So the term implies convert self-weight into masses. So as you can see, we can just convert self-weight into masses directly. So after converting the self-weight into masses, we can also add the self-weight. So adding the self-weight from load tab, there is a self-weight, making sure that it is dead load. So I can just add the -1 value along z-axis. As I have said before, z is the vertical direction. And after adding self-weight of your structure, you can also add the loads to masses. So sometimes we consider the 100% dead load as well as the 25% live load. So we can actually add here in the loads to masses. So after adding the loads to masses into our structure, so we can now define the load type. So from the assigned floor load, we can just define the floor load type. So for the name, let's say parking and structure. So base parking and ramps. So based on the design criteria, we will be using the dead load and live load of negative 3.15 pre-calculated before and the live load of negative 4.8. So I can now just add. So it is now reflected here in this dialog box. So after I have added the floor load type, I can now, so what's next to activate the second floor? So there is an activate by identifying here in MIDAS Gen. So I can just go to Storey and activate the second floor itself, considering the elements below it or connected to the second floor. So activate second floor. So I can now assign the floor load. So clicking this, assign floor load, selecting the parking and ramp. So there is a one-way load distribution as you can see into our structure. So there are no unmodeled sub-beams. And I can also copy the floor load. So here I can just copy it 3 times at 3.2 meters in distance. So I will now go to nodes defining loading area to actually apply the loads. So I will be starting from this node. So there you have it. We already applied the loading. So let us check if it is properly distributed. So load tab, and then there is a floor load. So I can just check the floor load. So it is now distributed along the carrying elements. So I can just uncheck it. So of course, we also have to apply the loadings into our ramps. So to apply the loadings to our ramps, same with the process that we did before, just nodes defining loading area now. And I can just select the nodes where I will apply the loadings. So it should be in a closed loop. So again, let us check if it is already applied. So there you have it. So after applying the floor loads into our structure, what's next is the lateral loads. So let us start with the wind loads. So for the wind loads, I will just add, considering IBC 2012. So basic wind speed, it is 250 kph, but as you can see, it is in miles per hour. I will just convert it or divide it into 1.6 to convert into miles per hour. Exposure category B. So since I am considering WLX, I will just change this into 0 along Y direction. So I can now click on apply. So for Y direction, I will just interchange the load factor for X and Y direction. So one factor or 100% will now be considered into wind load factor along Y. So I can now click on OK. So let me open that again. If you want to view the different profile of your structure, you can just see it in the wind load profile. And of course, you can just already check the calculation sheet. So checking on the make wind load calc sheet, it will now show you the calculation of MIDAS Gen. So this process is actually same with the seismic load. So I will just add the seismic load considering now the UBC 1997, and based on our design criteria, it is SD zone 4 and the closest distance is 10. And the structural parameter, let us just use the period calculator. The first one is for steel, the second is for concrete, and the last is for other structure. So since we are designing a steel structure, I can just select the first. And for the ductility coefficient R, so based on NSEP 2015 for the special concentrically braced frame, the R value that we will be considering is 6.0. So applying the 6.0 and the seismic load factor, direction factor along EQX, same with the wind load. So I am applying it into X direction. So I want it 100% in X direction and 0 in Y direction. So after that, I can now click on apply. So I will just change this into EQY. So interchange also the factor. So I can now just click on apply again. And we can also view the Storey shear force, the Storey shear, as well as how the structure calculates the whole forces or the forces into our structure without actually performing an analysis. So let me just close this. So after we have applied the static loads, we can also proceed with the dynamic loads. So for the dynamic loads, I will just go to dynamic loads, define an RS function. So I will just add an RS function here. And you can just simply import a file. If you have a ground acceleration or a ground data or a spectrum data, you can just import here. Or you can just copy and paste it here, just like in Excel. So what I will do is using the design spectrum based on UBC 1997. So same process or same parameters with the seismic load. I will be using SD, zone 4, and the rest will be the same. So as you can see, we already have plotted the response spectra of our structure. So I can now just click on OK. And after we have added the response spectrum, we can also add the response spectrum load case. So for the load case, I will just add RS along major. So for the direction, I will be using XY. And I can also use the auto search angle here in MIDAS Gen. So what are these auto search angle here in MIDAS Gen? So this is actually searching for the most critical axis of your building. So but this is actually based on conceptual rather than theoretical. So if you want to search the angle or the most critical angle of your structure, you can just use the auto search angle here in MIDAS Gen. So this is some of the strong points or the features of MIDAS Gen that we offer. So for the scale factor, this is actually I over R or importance factor over R. So sometimes engineers also apply the scaling here. So you can actually apply the scale factor of your response spectrum here. You can just multiply it to the factor that you need to scale up your response spectrum load case. You can just multiply it here. Or rather, you can just add it into the design load combination. So for the function name, since we have created one function, we can just check the function. And now we can now add the response spectrum load case. So adding in the different direction for the orthogonal direction, same factor. So I can now just add the response spectrum load case. So after we have added the response spectrum load case, so what we will do now is to add the analysis control. So I can just go to the analysis tab, eigenvalue. So let me use the rich vector analysis. So for the rich vector analysis, I can just consider all of the ground acceleration into our model. So for the number of generation, or I mean also the number of iteration that you can use the 10 value. So we can just add along X, Y, and Z direction. So after adding the analysis control into our structure, we can now perform the initial design. Okay, we forgot to actually view the whole structure, but it is okay. It will be considered also. So after we have performed the design, we can now view the results. So from the results tab, results table, we can just check the vibration mode shapes. So vibration mode shapes. So as you can see, this is the vibration mode shape of the structure or the modal participation masses printout. So along x-axis, it already reaches 98%. So in y-axis, on the fourth mode, it reaches 96%. So we satisfy the requirement of performing a dynamic analysis that it should reach at least 90% into our structure. So aside from that, we can also check if the structure rotates in the first mode or second mode. Here we can see that the third mode or the third mode in our structure, it now rotates. So for the period that we are going to use into our period bar analysis, we can actually update here the period analysis. Remember that we added a period per code before, so we can also update it for the period per analysis. Because actually in UBC and as well as in NSCP 2015, you can just compare the method A and method B, which is the from code as well as from analysis, and which will be the period of your structure that you will have to consider into your design. So here I can just update the period per analysis of the seismic. I can just use the first mode, which is 0.3972. So double click the load case 0.3972. So I can just change this into 0.3972 along x and y direction. So same with the EQY, EQX. So after we have updated the the period per analysis, so the software actually select which period of your structure will be considered. So for the fundamental period, it will now be considering this period, the 0.3972. It is now being considered. So there is a comparison, actually, the 1.3% of method A compared to the method B. So you can check it into the NSCP 2015 or in UBC 1997 as well. So after we have changed the period per analysis or added the period per analysis, we can also check the response spectrum. So remember that this response spectrum is rather it is conceptual rather than theoretical. So what we will do or what should we do if this angle actually change? So let's say it changes into 12 degrees. So if ever the angle changes, so we can just adjust the load direction factor in seismic load as follows. For EQX, you can just select the x direction and the cosine of the angle along major axis, and then you can just change the value or the specific factor in your seismic. So where is the specific factor of your seismic? Let me just stress this out. So these are the seismic load direction factor. So you will just change this if the excitation angle also changes into different degrees. So after we have updated and checked the excitation angle, we can just also get the static base shear of our structure. So again, I'm just opening a seismic load. So Storey shear, SRSS. So as you can see, we have 3163.9232. I have already created an Excel file. So this is 3163.9232, and the load case for the forces for the dynamic loads or the dynamic base shear, I can just go to the table results, Storey. So again, we have forgot that we have overwrite something here. So we can just also perform or reperform the analysis. So after reperforming the analysis, we can just view the dynamic base shear. So considering the response spectrum, so here I will be considering the without spring option for the shear force since I do not have a spring into our model. So I can just copy this, Control C from your keyboard and paste it here for the RS major as well as for the RS orthogonal. So for the SRSS, it is actually the square root of the sum of the square. So same with the above. So for the scale factor that you can use, there is actually a provision in NSCP as well as in UBC 1997 that if the structure is regular and you use the response spectrum or the ground motion based on the code, you can just use the 0.9 times the static over dynamic. So for the regular structure again, if you use the actual ground motion of the structure or you have the actual ground motion that you apply into your model, you can just simply use the 0.8 times static over dynamic. And if it is an irregular structure, you can just use the 100% of the static over dynamic for the scale factor. So here, by visual inspection only, but of course we have also to verify. I'm stressing this out again. We also have to verify different condition of our structure. I mean, the configuration. So we have to perform a specific or rather a comprehensive analysis here in our structure. But for the sake of this case study, I will just use the 0.9 of the static over the dynamic. So 0.9 static base shear over the dynamic base shear, and same with the above. So let's say we will be using a value of 1 for the scale factor. So that will be the scale factor that we will be using into the load cases of our structure. So after adding those parameters or after performing those type of calculation, we can now go to the load combination. So for the load combination, I can also use the auto generate. And for the code design, I will be using still AISC 15, LRFD 16. And the scale factor based on our calculation, we have 1.0 for both major and orthogonal axes. So I can now just add or click on OK. So the actual or the load combinations are now generated. So if you want to add different load combination, you can just go to the spreadsheet form. And from the spreadsheet form, you can just give a name, the activity, and the type. So for the type, if it is add, envelope, So absolute SRSS, and then for the factor you can just add the factor here. So now going to the steel design. So same with the steel design, I will just use the same factor for the response spectrum. I will now just click on OK. So going to the normal form. So this will be considered if we design our structure. So after adding the results or the load combination for the steel, we can simply check the different results based on the analysis. For example, for the reaction, so I will just select for example here a maximum strength, I mean service, let's say service, maximum service load along X, Y, and Z direction. So there is a red dot that is actually displayed. So I can just use the hidden. So I can just view the values as well as the legend. So let me fix the legend into 2. So which node is the maximum has the maximum reaction? It is maximum at node 47 and minimum at node 61. So this is the minimum reaction and the maximum reaction along X. So and different reaction along different direction. So aside from viewing the reaction, we can also view the deform shape. So selecting, of course, for example, EQX. So this is the deform shape of our structure for EQX direction or load combination. So our load case, sorry. And for the truss for the beam end diagram, we can also view the beam end diagram. Considering, for example, the load combination of maximum strength. We can also view the values at different location. So aside from that, we can also view the thrust forces. So which are in tension, which are in compression. You can now see the thrust forces also. So after viewing the different analysis result or post-processing result, so what we will do next is to design the structure. So first, let me go to the design tab. And from the design, I will just select the steel design. Then using the steel design code, so all beams, girders are laterally braced. So we'll be checking this since we have what do you call this steel deck which acts as a brace into our structure. We can also apply the special provision for seismic. As I have said before, we are considering a special concentrically braced frame. So I can now just click on OK. So of course, we also have to define the frame. So general design parameter, definition of frame. So we can also automatically calculate the effective length factors. We can also add the bending coefficient. So selecting all the beams. So let me just use the XY plane. And then selecting all the elements. For example, I want to apply that into beams. And then after that, after we have applied the CB, we can also add different factors like the member assignment. So this member assignment is also important if you want to allow single element member. So as you can see here in our structure, so it is divided actually based on the intermediate beam. So since we have created an intermediate beam, it will divide the specific girders. So if we want to find the result on a single element only, we can just use this member assignment. So selecting, for example, this one. So the element list from this one is actually here. So this means that the element 4 and 207 is now converted into element 4 alone. So it will now be element 4. So if we want to view the design results of this, it will now be showing only one element. So it will not be divided. So after we have applied different parameters, also you can also add different parameters into your structure. So if you want to check or to maximize your design, or I mean to evaluate more of your structure, you can add different factors into your model. So let me just proceed with the steel code check. Since I have already selected one, so I will just again steel code check for the whole structure. So we are now checking the steel structural members. So let me just unview the tour. So this is the result of the code checking that we have performed. Let me just expand this and select all the members. So let us check, for example, this one. So if we want to check the graphical result of this one, the girder, which is W18 by 71, we can now view different parameters based on the design. So we can now check if it is pass or fail. So if we want to view the detailed calculation, of course, we can just view the detailed considering the code into the analysis and design. So as you can see, this is how detailed MIDAS is, especially in representing the structural calculation. So the formula is also reflected as well as where to find into the code. So how about if we update a single element into our structure? So let's say I want to update this one because it is actually have a very small ratio, and I want to update the column. I want to change this into a smaller size, I mean. So what I will do now is to click the change, and I can actually set a specific combined ratio for the structure or for the element that I want to check, uh, considering this 0.8 to 1. I can just check which element or section passes using these combined ratios. So I can just search the satisfied section based on the results, and I can just, for example, I will be selecting W12 by 65 as my column, since it has a 0.941 steel ratio, combined steel ratio, and this the previous one is W14 by 120. So let me say I want to use the W12 by 65. So I can now click the change and close. So all of the columns in the W14 by 120 will now be changed into W12 by 65. So after changing that, I can now just update. Since I have chosen a different section, it should also consider the loads acting on it. What I mean is, we have to check whether the element pass based on the carrying loads. Since it already changes the stiffness, of course the loads will change also. So I can just select all the change properties. So the analysis and design results will be deleted. So it will now be considered into the design. So let me reanalyze again the structure. So this means that I am considering the 12 by 65 into the frame structure. And I will now just check or reanalyze this result based on the section that I have selected. So after analysis, of course, we have to perform recheck. So we have to recheck all the structural members connecting to those elements as well as this element that we have changed. So this is actually very good if we want to value engineer our steel section. You can just select smaller or larger combined ratio or the DCR if you want to value engineer your work. So here is the result. So as you can see, it now has the 0.896 considering the W12 by 65. But after doing the updating of the structural member, we can now see that there is a failure into our structure. So the brace. So the brace now failed. So let us check this one and investigate. So for the graphic, so let us view the graphical result. So as you can see, it now failed into axial strength and also the combined strength. So going back to the model, if you want to view the detailed analysis, why does the structure or why does the element fail? So we can just find where or how does it actually fail? How does the element fail? So from the detailed formula reflected here in the detailed result, you can now verify the element. So as you can see, the ratio is now failed. So it reaches or exceed 1.0, 1.044. So it depends on the engineer actually if he or she want to disregard this portion. If he or she wants to consider this DCR ratio, so it is actually up to him or her. So let me activate lastly the, for example, floor. And if I want to view the result, steel ratio, I can also view the steel ratio. So considering the combined, so I will just add the value. So as you can see, you can easily check the values or the DCR ratio. So if you want to be more specific of this, so code checking ratio, so this is what you will see. So the first is for bending, the next is for axial, and the third one is for the shear. So as you can see, we have a 0.05 for the bending, the DCR, 0 for the axial, and for the shear, it is 0.3. So again, we have to also remember that when we update a specific element, if we want to value engineer our structure, we should also always recheck our analysis, because even if the element passes along the specific element, some members are also affected due to the change in your structure. So that, I think, there you have it. So this case study is for studying purposes only, and the design or the designer or the structural engineer should also always verify and check the results as well as the input and output he made into a structural software. So if you have any more questions or concern, so you can just reach us to at philippines@midasit.com or at phinquiry@midasit.com. So that will be all. Thank you very much. Again, I am Engineer Marcos Pino, Technical Support Engineer from MIDAS IT Philippines.